Hello, Lambda School. Welcome to the C Programming Language 1. This lesson is your background material and starting training toward using the most popular system programming on Earth by leaps and bounds. C is such an important language that I have never heard of any other language being used for writing machine-level instructions for any CPU in my professional career. There are others. You can look up other languages that might be used for system-level programming. What I'm saying is that I have never met anyone who does it, and I've never met anyone who knows anyone who does it. So it's very important, and it is why there are a multitude of lessons here at Lambda School about C and its successor, C++. C is still in extensive use and very popular, but its use is limited. In the README for this, I go over what I think are the main uses of the C language, and that is for programming operating systems, number one. For programming systems that have small amounts of resources, number two. And let's see if I can see the other one. And for writing programs that have to be absolutely as fast as is physically possible on any medium. Those are the three uses for C. C was invented by a famous guy named Dennis Ritchie in the late 60s. He worked for Bell Labs, and he wrote C in order to write a new version of Unix, which they had been using at Bell Labs, and they needed an updated version. And the invention of C was in order to make Unix. So it is the bones of OS X and of Ubuntu. And I think it is the bones of Windows as well, fundamentally, and that there's no other base programming language being used in Windows, and that all the other higher level languages just come down to C, just like on Linux and OS X. So I'll say that again so that it comprehends better to you. Nothing you write on a computer does not become C eventually, or is not interpreted into something that is executed by C eventually. Your web browser runs in C. Your JavaScript application that runs in your web browser runs in C. Your internet, or rather your network interface card, communicates with your operating system through C. Your video games are written in C. It's all C. Everything is C. So it's an important language for you to learn, but it's only useful in the three instances that I gave to you above. But operating systems are foundational. That's why we've gone from basic operating systems lessons to basic C lessons, because you can't have an operating system without C today. Dennis Ritchie invented the programming language that operating systems are written in. And every program runs within an operating system, so you can't get away from it. I will talk to you about C++ in the future. C++ is the successor of C. It is a proper superset of C, which means that it has everything that C has, exactly, and also other stuff that's been tacked onto it. And the main purpose of C is for object-oriented programming. It provides an object-oriented wrapper over C, which C does not have at all, and can't be easily mimicked. And so C++ provides the ability to make objects, and it provides a big pile of standard libraries that prevent some of the common errors in C, But C++ doesn't make C easier. In fact, C++ makes C harder. Finally, C++ is really for writing video games. People learn it for a lot of other stuff, and they misuse it. It's also, very valid when you're trying to do high efficiency programming. But the literal fact is that C++ is not as efficient as C. C is the efficient one. C++ puts stuff on top of C that makes it less efficient. And even video games are moving away from using the technologies that are in C++. So we will also have classes on C++, but as with everything you learn at Lambda School, it's all context dependent. I always teach you that this technology is important, but it is actually only used for this and this and this. So if you're going to be making applications, if you're going to be programming servers, you will spend a smaller amount of time writing C, but you still need to know how it works. You need to not shy away if somebody says, write this thing in C for me, because then you become indispensable. Your ability to write a server application using Node, followed by a server application that uses a C library, you're indispensable. Now, and that's nobody's indispensable. And your company will fire you on the spot if they think that you're too expensive or if you get into a political battle with someone with more authority than you. But they will not let you go short of anything bad happening. As soon as you demonstrate your ability to master code through all the different layers of development. C is called a low-level language, which means that it actually controls the hardware that runs your computer. Every other language, except for assembly language and machine language, and possibly some other fringy system languages that aren't used by anyone I know or anyone I know who knows. There are others that can be lower level than C or equivalently low level to C, but you may not ever see them. So C effectively is the lowest level language. And JavaScript, in my opinion, is the highest level language because it is the most dynamic. It is the farthest from the machine. And JavaScript controls the machine through C, but it never makes code that's directly executable. What it does is it evaluates every line of code. And then that evaluation executes something in the machine, and then it evaluates the next line of code and decides what to do with the next level of the machine. So it never gets into this deterministic state. Deterministic is another thing that I wanted to demonstrate about C. When you have compiled a C program down to binary, to machine language, it is utterly deterministic in the sense that the program contained within that binary is a series of machine instructions that must execute in the order that they were compiled into. A JavaScript program, on the other hand, is not deterministic, meaning that the entire time that the program is running, anything can happen. In fact, including hilarious things like code injection. JavaScript gives you the ability to pass a string into the JavaScript program and then turn that string into an executable function and then execute it. So what happens on the next line in JavaScript is always a mystery, essentially, but not in C. All the other languages are higher level than C too. R, Python, Ruby, PHP, they're all based on C, essentially. They all make C calls. And the funny thing about this is that when you read historical literature about C, it tends to call it a high-level language. It says C is a high-level language that's really good for operating systems programming because it was the first successful language that wasn't assembly language that gave you total control over the machine. And the programming languages that came before C were all niche and fringe and used on a single platform and then dropped, although they philosophically inspired their successors. C, on the other hand, gave you the ability to program for any machine, so it was a high-level language. But now it's actually just the last level before it turns into machine-level instructions. I want to talk about the build process of C for a little while before I get into the C language itself. The build process involves multiple steps. With JavaScript, you write a JavaScript file and you pass it to your JavaScript interpreter, which could be Node or it could be a web browser. And the code is read letter by letter. It is read letter by letter, converted into executable in tokens, and then the JavaScript interpreter looks to see whether the thing that it's asking to do can even happen. And if it can't, then you get an error, your JavaScript program turns off. If it can, it does that thing and then executes the next line of code. With C, the code that you have written can't be executed. It is a pre-step that you pass to the compiler, which typically we call GCC or Clang. Clang is the OS X successor to GCC. And GCC is what is used on Linux. And I don't know about the C compiler on Windows. There was a popular one called Borland a long time ago, and I'm sure it's still in existence. I don't know what Microsoft uses for compiling their C code. I would be curious to find out and add it to a future piece of curriculum or lecture. All right, so when you have a C program, the first step that happens when you send it to GCC is something called pre-processing. And pre-processing actually looks at a whole nother language, which is linked to in the README, called the C preprocessor. And it's a whole nother language that you use to manipulate your C code during the preprocessor stage. And all the commands for the preprocessor start with a % sign, or rather a number sign, a pound sign. And those commands get evaluated by the preprocessor and turned into C code. The preprocessor reads the entire application, expresses all of the preprocessor instructions into C, and then creates a new file that is going to get used by the next step of the compiler. And I think I have a command in the README for doing that, which we will work through when we get to the real lecture. After it's been pre-processed, it gets compiled. And compiling takes the C code that you have written and converts it into assembly language, like real, actual assembly language that you could edit. You could open it up and change it. And compilation is actually comprised of two different steps that are part of the theory of language compiling. The first step is called lexing. And the lexer walks through your entire program, and it turns everything that you typed into a special symbol. And it just makes a list of them all. It makes a list of all the symbols, and it makes a list of all their references. And it puts that into a new file that's going to be used by the parser. All right, so then the parser is the next step. The parser iterates through your entire file, and using the symbols that were built in the lexer and matching them to the logical design that you put into your C code, it builds I need to look this up, actually. It's escaped my mind. It was cited to me by a friend of mine in a recent chat, and I've even got it open. I might be able to find it. It's like a static analysis graph. I'll look it up. Okay, so the parser takes all the tokens from the lexer and orders them and links them to one another, just like a linked list or just like a binary search tree. It makes a graph from the tokens to one another according to the rules of the C language. Okay, so these are the two places that you tend to get compiler errors from. The first compiler error can come from the lexer, when the lexer says, you used a token that's not permitted, or you used a token that you never specified anywhere, and it'll throw an error and say, you created a token and it's not a real token, and you have to fix your code so that the lexer can make a list of tokens that's correct. Then you get another error that says, from the parser, that says, you tried to cause a relationship from one token to the next that is not supported by the C language. And programming languages are essentially a set of parsing rules. It's like you can have a token that can point to another token of this type. You can have an int, and you can call a function on an int. And if you do that, it can return another int, or it can return nothing. And they build this vast, vast file a parsing file that says these are the rules that the language follows when it gets compiled. And when you run the compiling step, it essentially grabs a token from your program, walks it through the C programming language compiler's parser specification, finds the spot that it fits into, and then adds it to the graph of the program itself, which is going to get converted into assembly language at the end of the compiling step. After that, there's an assembly language program, which has been compiled for your, actually, I don't know, actually. I don't know whether the assembly language program that's been compiled is specific to your hardware platform's assembly language, or if it is a generalized C assembly language that then is going to get converted down into your hardware-specific machine language. That's an interesting question that you should look up after you listen to this lecture. So after you've done the parsing step, there's an assembly language file that contains the complete set of low-level instructions for creating your program and then executing it. And then there's, after that, one more step. And I want to say there's two more steps, actually. No, there are two more steps. So you've got this assembly language program. And there's an assembly step that you can execute separately in GCC that converts the assembly language, which is text, and it's human readable, but it's very low level. And we will have a lesson in assembly language coming up soon. The CPU language that you invented was, in fact, assembly language, but it was very simplified, and it wasn't presented in the way that assembly language is typically presented. All right, so the assembly step turns this assembly language program into a binary file. It assembles the assembly language into machine instructions. And again, I'm curious about the outcome of your research as to whether GCC produces machine-specific assembly or only machine-specific machine language. And that file that comes out of the assembly thing, you can't read it anymore. It's literally all ones and zeros, and it is a deterministic list of the ones and zero wire patterns that are going to go into the CPU in order to produce the output that you want. Magical, right? So when we do Hello World, that assembled program is about well, actually, I have to back that up because there's a step that I haven't gotten to yet called linking. So once the assembled machine language file has been created, the compiler looks at all the other C files that the one that you just assembled might depend on, and it inserts into that file, the one that you just assembled, all of the external libraries, all of the functions and all of the functionality that you brought into your program using the #include command, which is a preprocessor directive that copies code out of that file and pastes it into your file prior to compiling it. So there's binary code somewhere for that included data that has to get inserted into your executable file so that it can run. That's called the linking step. And that is another standalone step with GCC that has to be written correctly in order to build healthy C programs. So once that finally linked program has been built, we looked at Hello World, and I gave you a fairly long assignment in just exercising basic C structs, working through compiler errors, and working through the dev, compile, test loop, which is the most common loop that you will encounter in software development. You write some code, you compile the code, or you lint the code, and then you test it, and you say, did it work or not? And then you go back, and you dev some more, and you compile some more, and you test some more, and you go around like that until your program works. The Hello World program that we wrote is 8,400 bytes, if I remember correctly. Okay, so the Hello World that we wrote is, well, that would be an interesting thing to look up, and maybe we can look it up inside of the full topic lecture. The Hello World file has a specific size in assembly, but in assembly, an assembly program is much larger than a binary program is, because each assembly instruction, which is a series of characters, gets converted into a single word in order to be communicated to the CPU. So anyway, all I was getting at was that our Hello World program ends up becoming 8,400 bytes. It's 8,400 bytes of binary. And because we have 64-bit CPUs in general, those are 8 bytes per instruction, generally. It's 8,400 bytes, which turns into 1,050 instructions in binary contained in that file. And that is the entirety of the program. And it's perfectly easy to create a 100 megabyte C binary by importing libraries and using more complicated functionality. Streaming video or complicated data structures involve lots of external files as well. And so in that case, you are talking about 12 million separate 8-byte instructions. Okay, so you've got a general overview of what C is. You're ready to talk about it and imagine what it is. And you've written a really simple program. So I want to go to screen sharing now, and I want to rap about C again. I have been expanding the full C lesson. And there's a lot of material to cover. And I'm going to get started here, and then I'm going to come back around to this during your full lesson. And we might have 2 full lessons in order to see if we can cover all this material. Because without knowing all of these details, you can't claim to know how to write C. You won't be able to write all this stuff off the top of your head, just as I am not. But you will be able to look it up, and the words will make sense to you. Okay, so I'm going to go through the list in our intro to topic, and then we will try to develop and go in more detail as far as we can during this lesson. We're going to have a second lesson on C that's going to involve trying to capture the rest of it and some challenges in actually trying to use C in development. All right, so the first item, so in the top of this file, this was your original program. Primitives, loops, break, continue, branches, if, else, if, while. While doesn't go with branches. Arrays and structs. I say to become classes, they become classes in C++. They have effectively the exact same functionality as classes in C++. But in C, there is no such thing as a class. And so struct is what you're stuck with. All right, so the rest of C you're going to have to learn in many more courses, starting with this one today. The first item I have here is extended types. All right, you could look this up. You could Google C extended types. You learned the basic types up above: int, char, float, double. And there are dozens and dozens of other platform-defined types. The first one you might consider is a signed or unsigned int. You can have an int that has a minus sign or a plus sign optionally, or one that only has a plus sign. You can have a long int, which means that it's actually got twice as much precision as an int does, and it can store a much bigger number than an int. You can have a long int or a long unsigned int. You can have a long unsigned int. You can have an unsigned character. You can have, oh gosh, I had a crazy list of this, and I won't go into it any more deeply because there's a lot to talk about. The thing that you need to know about these extended types is that they're all system defined, like they're platform specific, and that each one of them is more or less just a macro that says use 2 ints or use 3 ints and process it a different way. And on many systems, you can define them yourself. Something that you will see fairly often is something like this: uint32 myint equals 5. And this means that someone specified exactly what uint32 should be on this code base, because it changes from system to system. And one of the many parts of making a C program run on different architectures involves making sure that all of their types have the same length and the same behavior. We're going to learn about pointers. references, dereferences, and pass by value. This is the great strength of C. This is what makes C become so efficient. A pointer is a memory address, and you can create an object or a type in C, and then you can call it a pointer type instead of a specific type. So like an int, you can make an integer x equals 5, and you can make, let me type this in, int x equals 5, and you can make a pointer to an integer x, and you can assign it to something. But this command might not actually work, and I can't test it trivially. Actually, I will test it trivially because I really want to. We'll come back to it in the main curriculum, actually, instead of getting stuck. Okay, because the reason that I'm balking about this is because a pointer to an integer is effectively just an integer. It is actually an integer that's as big as your system's memory bus is. And it can reference any value in your memory bus. It's not a value. Int x, x is equal to 5. But an integer pointer that points to x is actually equal to the memory address. And in order to get a 5 there, so this may work. This may be syntactic sugar that figures out what I want to do and puts a 5 in the memory that's located at the address pointed to by x. But there's another way that you have to do it if you use, for example, a more complicated structure. Let's call it, struct mystruct equals, you just define it. Oh, it needs to be a pointer. Mystruct pointer y. Okay, and then when you want to actually assign data to y, you have to, it's called dereference it. You have to convert it from a pointer back into an object and then assign a value to it. And this code won't execute either because struct mystruct is not an integer, and I'm trying to assign an integer to it, so that's going to give me a problem. And then it goes on from here, and we'll try to cover this in more detail. You can take a value like int x, and you can turn it into a reference, which makes it do something differently by saying reference to x. Okay, but you can't assign a reference to x. You could make a new one like this. And you can finally, well, I'll come back around to this. The last detail that you need to know about this is that functions in C, if you pass a primitive type, like an integer, they make a copy of it. So if you pass in an integer here, arg is going to be a copy of whatever was inside of the call, if we call it next on the next line, functions 10. The 10 here, 10 remains, oh, hello, in this scope, and arg above is a copy of 10. Okay, so if you change it, the changes are lost when the scope exits. The only way that you can pass a value from one function to another is to make it a pointer. Then you can change the value that is pointed to by the pointer, and the pointer remains the same, remember, because it was copied when it was passed in. All right, memory management is a huge, huge deal in C, and it's one of its great strengths. There's a function called malloc, and what you do is you pass it in a size. You say, I want to malloc this much memory, and you make a pointer equal to it. Now, we can't do this with an integer pointer because an integer, well, actually we can. What we end up with is an array of integers. So if we say integer pointer x equals malloc, and then I want to say size of, well, I can just give it a number, 1024. That is now an array of integers that's 1024 bytes long. And that array will never be freed. The operating system has given us 1,000 bytes to store integers in, and we can store anything we want in there, which is one of the ways that C becomes very hard to understand. We don't have to store integers in there. We can pack any arbitrary bytes we like inside, though the compiler will try to keep us from doing it. That memory, the operating system has created a special allocation for our program, and it will remain allocated until we say free x. And if we don't do that, then our program will obtain something called a memory leak. We can crash our program by freeing x twice. And we can leak memory by allocating memory twice. This memory becomes unrecoverable. And it's the memory above that's unrecoverably leaked. There's no way to get it back if you make this mistake. If you have a memory leak in your program, which you may have heard before, eventually your program will crash because the operating system will run out of memory that your program has access to be allocated. And the next time you say, hey, operating system, give me another kilobyte, the operating system says, you're cut off. In fact, you're cut off so hard, I'm going to power you down. It's possible to write something called a signal handler that will prevent your program from powering down if it runs out of memory. But that's advanced C that we will only equivocate about in the operating systems calls class. And you will have to exercise it on your own. It's a substantial lesson. All right, const. Const is a modifier of a type. So you can say const int equals 5. And now, or constant 5 equals 5, and 5 cannot be changed. The compiler will check your behavior using the integer 5, and if you try to reassign it, it will break the compilation and tell you attempted to do something that you explicitly told the compiler is not allowed. So you've been exposed to this in JavaScript, and something that is shared between JavaScript and C is that only the thing that you are directly consting gets const. If you do something like const struct mystruct, then you can change the values inside of mystruct, but you can't change mystruct. You can't reassign it. And then things can get particularly complicated when you want to const a pointer to a number. Because what we've done here is we've actually made the pointer const. You can't change the pointer, but you can still change the value. And you have to type crazy things like this in order to make the value totally unchangeable. And this is not the only, you can also do one of these where you can say, where the pointer can be changed, but the value that's pointed to here can't be changed. So this gets, it gets continually more complicated. All right, so reading from files is big in C. That's because C is the only systems programming language. It's the only language that actually knows how to tell the operating system, create a new file, insert it in the file table, and allocate disk storage for the data I'm going to put in it. It's the only programming language that can tell the operating system that file should be deleted. Okay, now I'm being overly specific because Python is much, much better at creating and deleting files than C is, but it's using C to do that. Okay, so that's what a higher level language means. It uses C to do something more easily than C does. But you need to know the rules of reading from files in C. And even better, we are going to learn how to read from standard in with C, which gives you essentially the ability to create Unix applications. The way that the Unix software model works is that files read from standard in and write to standard out, and you can chain them together and produce amazing libraries, incredibly powerful system utilities, and that involves reading from standard in. So we will spend some time reading from files. Metaprogramming. Metaprogramming is serious business and not something that I can cover in an entire program. But I'm going to show you this interesting file called it's user/local/include/mysql/myglobal.h. And there are a great many files like this on your system, but this one I found. And it uses the preprocessor language to configure the compilation of MySQL to work on any platform. It says here, if you're running Cygwin, you need to delete all the Windows defs that have been created by other software components that are part of the C compiler. It says undefined Windows, because if their software finds Windows, it's going to do something different that's going to break it inside of Cygwin. And this goes on and on. This file, we have not seen one line of the C programming language yet. This is C, theoretically. And this is C. We found one. This says, define a function called myoffT2double that replaces any function called my ulong2double, and then insert this code anywhere that that function gets called. And this is called an inline function. It means it gets put one time at the head of the file and it's used by everything else. And this just goes on and on. It's actually 1,200 lines of almost completely compiler macros, preprocessor directives that configure the code prior to its compilation so that it works on different platforms. That's what it is for. And a huge percentage of C programming professionally is getting your code to work on the platform that you are currently working on. If you are a Linux user, if you install a program without using apt-get or dpackage or whatever it is you've got for your Linux instance distro, then you have to work through the C code of the program that you are trying to install so that it will compile. And it's intensely difficult, and it's why apt-get is around. All right, so I am going to teach you how to do this if-def metaprogramming. We're not going to write programs in it, but we are going to look into the bowels of the C compilation process because you can't do C programming without understanding it. And you don't understand C if you're not ready to follow a chain of files through if-defs in order to figure out why one particular program doesn't work. Okay, these four go together: declaration, definition, initialization, and forward declaration. And they're just specifics on the ways that you can create and reference variables inside of C. I'm not going to get richly into them at this time. I've included a link to forward declaration of structs, which turns into a very messy syntax that I think has been mostly cured by the modern C compilers. And so hopefully you won't even need to learn this bit about struct forward declaration. Faults. Faults are operating system messages that can be delivered to your C program, because effectively your C program is an operating system program. That's what happens when you write C, is you make a file that gets linked into the operating system that you're running it on's life cycle. And that's how the operating system pauses your process and then resumes your process when its turn is to resume again, which you'll be practicing next week in great detail. Okay, so when your program does something that the operating system has deemed to be against the rules, a fault is sent to your program using a signal. And the signal is an operating system call that we will look at briefly in our operating systems course that enables the operating system. So by default, most of the operating system calls just terminate your program. But you can write a handler that will allow you to handle the operating system calls. Header files are those programs that end with .h. When you say include math.h. And they're very interesting. They are declarations. Okay, up here we're going to talk about declarations. And what a header file does is it defines a contract for code that has been compiled somewhere else and put away. And it allows the compiler to read that header file in and then assemble your program without even having access to the code that your program depends upon. Okay, so you can receive, for example, math.h, you can receive a library from another vendor, and they will give you an object file. And it might even be encrypted. It might be DRM'd and encrypted and be totally next to impossible for you to actually figure out the code inside of that file. But they will give you a header file that goes with it that specifies the contract for how that file behaves. Then you can write code using the functions and the objects inside of that header file and compile it, as long as you link the binary that they sent you that you can't read into it. So this is the basis of sharing code and building larger programs in C. When you include a file in C, the compiler, it's actually the preprocessor, as you can see, it's a preprocessor command, goes out and finds that file and then literally pastes that file into your file right before it begins to compile it. So it injects all the code that you specify with include into your file and then treats it as though it's native code. I feel like this is a pretty satisfying topic lecture at this time, and that it leads you down plenty of paths if you wish to. And so I'm going to leave you with this. I made a copy of this and I started putting details into it. And so I'll continue working on that. But right now, I want you to read this list that comes after and ponder all of these different details before we get into the main lecture, which is coming up in a few hours. Thanks, Lambda School. I will see you all very soon. This has been the intro to topic lecture for the C programming language 1.